somewhere off the coast of West Antarctica. A slab of floating ice, the last thing physically holding back a glacier the size of Florida, is now expected to break apart within months. Not within decades, not within centuries, months. The glacier behind it, Thwaites, nicknamed the Doomsday Glacier for good reason, contains enough ice on its own to raise global sea levels by about 26 inches if it were to fully collapse. And new satellite tracking suggests the last natural break holding it in place is about to give out. Today, we're going to break down exactly what scientists have found, why an ice shelf breaking apart matters, even though it's already floating in the ocean, and what this actually means for the timeline of one of the most consequential glaciers on the planet. No guessing, no dramatizing, just the facts, the data, and what it actually means. Before we get into it, I want to ask you something. If you live in a coastal city, have you ever thought about what a place like Antarctica, thousands of miles away, actually has to do with your own shoreline? Drop your city in the comments, because by the end of this video, the connection is going to be obvious. If you want to be the first to know every time the data on this shifts, subscribe. It's completely free, and it genuinely helps this channel keep going. Let's go for 5,000 likes on this one, so the algorithm shows it to more people who need to understand exactly what's happening at the bottom of the world. Thank you. Now, let's get into it. First, a distinction that almost every headline on this topic gets muddled, and understanding it is the key to understanding everything else in this story. Thwaites Glacier itself is a 2-kilometer thick river of ice sitting on land, part of the West Antarctic ice sheet, grounded on bedrock beneath it. In front of that glacier, where it meets the ocean, sits something different, the Thwaites Eastern Ice Shelf, a 350-meter thick slab of ice that has already broken off the front of the glacier and is floating on the ocean surface. Because it's already floating, its potential loss doesn't directly raise sea levels on its own, the same way an ice cube already floating in a glass doesn't raise the water level when it melts. What that floating shelf actually does is act like a cork in a bottle, or a giant retaining wall, physically pinned in place at one specific point where the seabed rises up to meet it, called a grounding point. As long as that shelf stays wedged against that pinning point, it pushes back against the glacier behind it, slowing the rate at which that 2-kilometer thick wall of land ice can flow into the ocean. Lose the shelf, and you don't lose ice directly. You lose the brake pedal on everything behind it. According to Robert Larder, a marine geophysicist with the British Antarctic Survey who coordinates the UK side of the International Thwaites Glacier collaboration, the joint research effort between the US and UK studying this exact glacier, the situation has now reached a critical point. Larder has stated plainly that this final section of ice shelf is poised to disintegrate. That's not a throwaway line from a press release. That's the assessment of one of the scientists most directly responsible for tracking this glacier's behavior in real time. According to his monitoring, movement on the western side of the shelf, where the ice is actively breaking away, has roughly doubled over just the past 8 months. When a floating slab of ice starts accelerating its own breakup at that pace, scientists start treating a full disintegration not as a distant possibility, but as something that could plausibly happen within the current year. This didn't come out of nowhere. A study published in the Journal of Geophysical Research, Earth Surface, led by researchers at the University of Manitoba's Center for Earth Observation Science, traced 2 full decades of satellite data, from 2002 to 2022, to map exactly how this ice shelf has been coming apart from the inside. What they found was a specific, narrow band of ice called a shear zone, sitting just upstream of that critical pinning point we mentioned earlier, where different sections of the shelf have been sliding past each other at different speeds, stretching and tearing the ice the way you'd stretch taffy until it splits. The researchers documented this weakening unfolding in 4 distinct phases, starting with long fractures running parallel to the direction of ice flow, cutting straight through that shear zone. Over those 2 decades, the total length of fractures across the shelf grew from roughly 100 miles to over 200 miles. And here's the detail that genuinely concerned the research team. Even as the total fracture length grew, the average length of individual fractures actually decreased, meaning the ice wasn't just cracking more, it was cracking into a larger number of smaller, more numerous fragments, a pattern consistent with a structure that's becoming progressively more unstable rather than settling into a new equilibrium. There's also something happening below the waterline that compounds this. A separate team of researchers has been tracking how warm ocean water actually reaches the underside of shelves like this one, and what they found is a genuinely nasty feedback loop. As warmer, saltier ocean water works its way beneath the ice, it mixes with the colder meltwater coming directly off the shelf, and that mixing generates turbulence, powerful swirling eddies of water up to 6 miles across. That turbulence doesn't just sit there, it actively works to melt even more ice from below, which then produces more cold meltwater, which mixes with more warm water, which generates more turbulence. Once a feedback loop like that gets established, it tends to reinforce itself. And researchers studying it have explicitly warned that it could intensify further as ocean temperatures continue to rise. So let's talk about what actually happens if or when this last section of shelf lets go. To be clear about the timeline here, researchers are not saying Thwaites Glacier itself is about to slide into the ocean next year. Modeling this kind of collapse is genuinely difficult, and the honest scientific consensus is that a full collapse of the glacier would unfold over decades, quite possibly centuries. But losing the brake doesn't mean nothing changes in the meantime. It means the car starts rolling faster down the hill it was already on. A study published in March in the journal Geophysical Research Letters, using 2 independent ice sheet models calibrated against 13 years of real observed data from Thwaites between 2004 and 2017, projected the glacier's ice loss forward to the year 2067. What they found is that Thwaites could be losing somewhere between 180 and 200 billion tons of ice per year by the 2060s, a rate that on its own would be roughly equivalent to the total ice loss currently happening across the entire Antarctic continent combined. And in a detail the study's authors specifically flagged as concerning, the individual models that most closely matched what's actually been observed on the ground so far were also the models that projected the highest future losses. Meaning reality, so far, has been tracking toward the more severe end of the range rather than the more conservative one. Now, it's worth being fair and including the other side of this scientific debate, because that's exactly what separates real reporting from fear-based content. Not every study agrees on how urgently this specific ice shelf's collapse matters. A 2023 study, published in Geophysical Research Letters by Gudmundsson and colleagues, used 3 separate ice flow models to directly test how much the upstream glacier is actually being braced by this shelf, and concluded that a complete disintegration of the ice shelf would not substantially impact Thwaites' overall mass loss over the following 50 years. In other words, that specific research team's modeling suggested the shelf's structural support matters less than some of the more alarming framing implies. This is a genuinely unresolved scientific question, and it's exactly the kind of nuance a headline can't hold. What nearly everyone studying this glacier does agree on is that Thwaites overall has been retreating at an accelerating pace for decades, and that watching how this shelf behaves in the coming months gives scientists a real-time test of which set of models is actually tracking reality most accurately. Here's why any of this matters beyond Thwaites itself. Scientists describe Thwaites as a keystone glacier, meaning it doesn't just matter for its own ice, it physically helps hold neighboring glaciers in place across the wider West Antarctic ice sheet. If Thwaites retreats far enough, researchers warn it could destabilize those surrounding glaciers as well, effectively pulling out one support beam that was helping hold up several others at once. Thwaites alone contains enough ice to raise global sea levels by roughly 65 centimeters, about 26 inches. But the broader West Antarctic ice sheet that it helps anchor contains enough ice to raise global sea levels by around 3 meters, nearly 10 feet, if enough of it were eventually destabilized. Coastal impact researchers have estimated that 3 meters of global sea level rise would be enough to displace somewhere between 500 million and 1 billion people from coastal areas, depending heavily on how quickly and how well coastal defenses are built up in the meantime. That list of exposed places isn't limited to remote, low-lying nations either. It includes some of the most economically significant cities on the planet: New York, Miami, London, Shanghai, Tokyo. It's also worth understanding why scientists are only now getting this clearer picture, because the tools available to study Antarctica have genuinely transformed in just the last year. In 2025, researchers published an updated topographical map of the entire Antarctic bedrock called BedMap 3, incorporating 84 additional airborne geophysical surveys, roughly 52 million new measurement points, and nearly 1.9 million kilometers of radar survey lines. That map revealed just how much of West Antarctica's ice sits in deep basins extending below sea level, a configuration that makes it far easier for warm ocean water to work its way underneath the ice from the sides, accelerating retreat in ways a simpler, flatter bedrock model wouldn't predict. Separately, a newer climate modeling project called PolarRes combined 4 state-of-the-art regional climate models at roughly 11-kilometer resolution, specifically tuned to Antarctica's uniquely complex coastal weather, giving researchers a far more detailed picture of exactly how local winds, snowfall, and ocean interactions are shaping individual glaciers, rather than relying on lower-resolution global models that tend to blur these details together. It's worth understanding one more distinction that matters enormously for this story: the difference between East and West Antarctica, because they are not equally vulnerable to what's happening at Thwaites. East Antarctica, the larger of the continent's 2 halves, largely sits on bedrock that remains above sea level, meaning the ice there is fundamentally more stable, anchored on high ground the way a glacier in the Alps sits on a mountain, rather than floating over a submerged basin. West Antarctica, where Thwaites sits, is a different story entirely. Much of it occupies deep basins that extend far below sea level, some dropping more than 2 kilometers beneath the ocean surface even before you account for the ice sitting on top. That configuration is what makes West Antarctica's ice sheet fundamentally more exposed, because warm ocean water can work its way into those deep basins from the sides, attacking the ice from underneath and from the edges, simultaneously in a way that simply isn't possible where the bedrock sits above sea level. This is exactly why the scientific community's attention keeps returning to this specific corner of the continent rather than treating all of Antarctica as a single uniform system. The geology itself makes West Antarctica the genuinely vulnerable half. It's also worth appreciating just how long scientists have actually been watching this specific glacier, because Thwaites hasn't suddenly appeared on researchers' radar. It's been a subject of serious concern for well over a decade. Back in 2014, researchers already documented that the glacier's flow speed had doubled over the preceding 3 decades, a warning sign that prompted the formation of the international Thwaites Glacier collaboration itself, a dedicated multi-year, multi-million-dollar joint research program between the U.S. National Science Foundation and the UK's Natural Environment Research Council, specifically created to understand this one glacier in detail. That collaboration has sent multiple research expeditions directly onto and beneath the ice over the years, including underwater robotic vehicles piloted beneath the ice shelf itself to directly measure water temperature, salinity, and melt rates at the exact boundary where warm ocean water meets the ice from below. The scale of scientific investment poured into understanding this single glacier over the past decade reflects just how seriously the research community has treated it, long before headlines about a 2026 ice shelf collapse started circulating. What's changed recently isn't that scientists suddenly discovered a new problem. It's that a problem they've been carefully tracking for over 10 years has now reached the specific threshold Robert Larder and his colleagues have been watching for. There's also a broader sea level context worth understanding here, because Thwaites is one very significant piece of a much larger accelerating trend. Global sea levels have risen by an average of about 2 millimeters per year since 1960, but that rate has nearly doubled in recent decades, reaching roughly 4 millimeters per year between 2005 and 2023. For most of that 60-year record, ocean warming itself, water physically expanding as it heats up, a process called thermal expansion, has been the single largest contributor, responsible for around 43% of total sea level rise. Our oceans absorb roughly 90% of the excess heat trapped by greenhouse gases, and since oceans cover more than 70% of the planet's surface, even a small amount of warming translates into an enormous volume of thermal expansion. But researchers tracking this budget have found something notable. Since the 1990s, the balance has been shifting, with accelerating ice loss from Greenland, Antarctica, and mountain glaciers becoming an increasingly dominant driver of sea level rise, rather than thermal expansion alone. In other words, the system is gradually shifting from being driven mostly by warming water to being driven increasingly by actual physical ice loss from land, exactly the kind of ice loss Thwaites represents. So where does that leave us? This isn't a story about Antarctica collapsing into the ocean next week, and treating it that way would genuinely misrepresent what the science actually shows. It's a story about scientists gradually replacing estimation with direct observation year after year, and finding that the ice sheet responds to a warming ocean with more sensitivity and more complexity than earlier, simpler models assumed. The last natural break on one of the most consequential glaciers on the planet appears to be failing, possibly within months rather than years. That doesn't guarantee a specific timeline for what comes next. The honest scientific answer remains that the glacier's full collapse would still unfold over decades or centuries. But it does mean the process is now measurably accelerating, tracked in real time by researchers who will be watching exactly how this ice shelf behaves over the coming months. We'll keep following this story closely and bring you an update the moment the shelf's condition meaningfully changes, or the moment new modeling data comes in. If this kind of grounded, fact-first coverage of the science shaping our planet is something you want more of, subscribing genuinely helps this channel keep making it. Let's try to hit 5,000 likes on this one together. Thank you so much for watching this. Stay curious, stay informed, and I will see you in the next one.